As usual, let me just start off with a review of what we did last time before moving on, because we covered a lot of material that's you've never seen before. Okay, so we did the historical review of sort of all the different eras of quantum transport leading up to where we are now, what I call the 2D materials era. And probably the most important concept we introduced is this picture of the device in the scattering states. And also, I guess something I didn't emphasize is the concept of an open system, where our device is some small finite region that we're interested in, but we have these semi-infinite left and right contacts that act as thermodynamic reservoirs, and from them you're injecting plane waves into the device. Part of them are going to be reflected, part of them are going to be transmitted, and so quantum transport through devices is just like the scattering problem that's set up in physics, where they look at a scattering wave coming off of some scattering potential, except now our scattering potential is a device. And so you, just like in the physics problem where you inject a plane wave at some scattering potential, now you inject a plane wave at your device. The device is your scattering potential. Some of it's going to be reflected, some of it's going to be transmitted, and our job is to figure out what is transmitted, and that determines your current. And so the basis that we use are scattering states. And this is also called the scattering state picture, in which I've just kind of made one slide. This is the crucial picture to keep in mind, because even when we do coherent green functions for the whole many first chapters of the course, this is a problem we're solving. This is all we're going to be doing, but we're going to be doing it with green functions. But what we understand from the wave function point of view, this is just another way of doing it. And so this is a picture of injecting a plane wave. Some of it will be transmitted, some of it will be reflected, and some of it will be, some wave function in your device. That wave function in the device is one of the things we're going to need when we calculate current density. So this is the scattering state picture. The scattering states also serve as a basis. If we go from the more abstract picture to the more concrete picture of actually a band structure like down below, this is what it would look in terms of, say, some arbitrary conduction band, where you've applied a bias across the device, so the conduction band on the right is lower than the conduction band on the left, and everything we're doing is coherent transport, which means it's elastic, which means total energy is conserved. So if I inject a plane wave device from the left, it comes across the device, total energy is conserved in this picture, right? The kinetic plus potential energy is conserved. And so when it reflects over here in the left contact, since by definition if it's or left lead, there's no potential variation over there. So it stays at the same energy, it just reverses direction, so K goes to negative K. And part of it gets transmitted at the same energy, but the K can be different because it can have a different kinetic energy when it comes out the other side, because there's a bias applied. And you can inject from both the left and the right. So up top, we're injecting from the left. Down below here at the bottom, we're injecting from the right side. Okay. That set of states that are generated when you inject from all the left K vectors and all the right K vectors, they form the scattering state basis. And that's the basis that we are using, even though it's not. When you do this transport, that's sort of the basis that underlies the whole picture. What I've written here in this curly brackets, so this total collection of the left and the right in scattering states that are created by injecting a left or right moving plane wave from either the left contact or the right contact. They form a complete, and if you normalize them correctly, orthonormal basis. The only thing that might be missing is if you have bound states, but we don't need to worry about them for everything we're going to be doing. Current continuity. So is formulated in terms of flux, and flux is density times velocity. And so for a wave function, the density is like psi squared. So the flux is psi squared times the velocity of that wave. So the injected wave, which is just this exponential, this guy here, its flux is just its velocity, and the psi squared is just 1, right? So its flux is just its velocity. And the reflected wave, well, it's the velocity times this magnitude squared of the reflection amplitude, RL squared. That's the reflected flux. And the same for the transmitted flux is coming out the right-hand side. It's the velocity on the right side times the magnitude of the transmitted wave amplitude squared. That's the transmitted flux. And so by basic current continuity, flux continuity, you have this continuity equation where the injected flux minus the reflected flux has got to equal the transmitted flux. And so if we write that over here, we're going to see that these terms over here in this blue box on the right-hand side, what's on the right-hand side is actually our transmission probability, and what's on the left-hand side is 1 minus our reflection probability. So these just come about by current continuity. So the definition of the transmission coefficient, the fundamental definition, is just the ratio of the transmitted flux divided by the incident flux. That's your transmission probability. And that's equal to, well, we just went through it. The transmitted flux is velocity on the right times is t squared. The incident flux is just velocity on the left. You take the ratio, and that's your transmission probability. And it's going to be the same whether you, for a given energy, the same whether you inject from the left or the right. The reflection probability is defined in the same way, the reflected flux divided by the incident flux. And, well, over here, since they're both at the same velocities, that the velocity cancels for the reflection probability, and you just have that it's just equal to the magnitude of that reflection amplitude squared. And so this fundamental expression, t plus r equals 1, just comes out of that equation we were just looking at from that conservation of flux equation we wrote down just back in this blue box here. This guy here down at the bottom right. Hello, bottom. It's a delay. Bottom right. Okay, down at the bottom right. That was our, equation for conservation of flux. And so this t plus r equals 1 comes out of this equation over here in the left red box. That's the same equation. It's just a statement of conservation of flux. That the transmitted flux plus the reflected flux has got to all be accounted for. It's got to be equal to 1. Okay, so those are your transmission and reflection coefficients. So that's the continuum picture. And then we went through and just reformulated it in terms of the picture that wow, that's a big delay. There we go. That we came to know and love last quarter. It's tight binding picture. So this is figure 1.2 from the notes. It's just what I drew in class by hand, but I thought it would be nice to put a cleaner picture in here. So that we formulated the problem in this tight binding picture, same, we have the left lead, the right lead, the device region, and we just set it up in terms of tight binding. We know what the in the localized orbital basis, we know what the Hamiltonian for this system looks like. It looks like this, right? It's an infinite crystal. So this tridiagonal Hamiltonian just goes on forever. This is figure 1.3 of the notes, okay? This tridiagonal Hamiltonian is what these dots on the upper left and lower right represent. It just goes on forever, infinitely tridiagonal. But it's divided up in these regions corresponding to the lead, left lead, the right lead, and the device. And there's no, as we drew before, in the left lead and the right lead, there's no potential variation, no macroscopic electric field. And so we can write the general form of the wave function out there and the general form of the wave function in the right lead. And what we need to solve for is what's going on in the device. What we're after, what we're interested in, is the wave function in the device, because from psi squared we get the electron density in the device, and then we can feed that into Poisson's equation and do some kind of self-consistent calculation. So we need to solve the device part of this to get the electron density and the current. But it's an infinite matrix, so the whole problem is how do you just get the device part without worrying about those two semi-infinite regions on the left and the right. And we dealt with that by, well, first of all, just look, here's row 1. Down at the bottom in blue is the equation that results from row 1 of the matrix. So row 1 of the matrix, we're looking at this row right here, row 1, right? So that's row 1 of the matrix, and you can see all the terms there that go into the blue equation at the bottom of the page. I just take that vector, multiply by that matrix, and row 1 gives me that equation in blue, right? Everyone see that? And going back and forth between matrices and the actual equations they represent sometimes. People aren't used to doing that. But so row 1, and similarly row 3 in green is the equation that results from row 3. So here's row 3 down here. And the equation at the bottom in green is the equation that results from row 3 of that matrix equation, where I've just moved, I moved this, the E times the C1 or C3 over to the left-hand side. It's a homogeneous equation, right? Every term is multiplied by a C sub I of some C, and it's your eigenvalue equation. And as I said, we just want to solve for C1, C2, and C3. That's all we care about. But the equation for C1 couples to C0, which is that semi-infinite region. And the equation for C3 couples to C4, which is the other semi-infinite region. And so if I write a new equation for C4, that couples to C5, et cetera, et cetera. So it's just an infinite hierarchy of equations, so you have to figure out how to truncate somehow. And the way we did that was to write down this general form for the wave function in the left lead. So in our tight binding representation, this is the general form for the wave function in the left lead. It looks just like what we wrote down for the continuum, except we had like e to the I klx, or e to the I kl x minus x sub l, and e to the minus I kl x minus x sub l, right, in the continuum when we wrote it down in just for the continuous wave function. Does everyone feel happy with that? This is what it looks like in the tight binding representation. This state in the left lead. Before we had written down something like the state in the left lead was e to the I KL, what, x minus x sub L plus R sub L e minus I K L x minus XL. Right, that's what it looked like in just for our continuous wave function. So is it clear that this is what the equation up top is what it should be for the tight binding representation? Or let me put it another way: is there anything not clear? Is there anything not clear about the equation at the top? Why is this here, for example? Why, instead of just having these components over here, like when I write it in the continuum representation, I just have this, I'm not multiplying by any ket. Well, I guess, in general, right, when you go to this tight binding basis, any psi, the form of any psi is sum over n, C sub n, whatever your basis is. And so this thing in the brackets is my C sub n. Let's see, did I write that out somewhere? This thing in the brackets is my C sub n. Or I wrote it again over here. So this is that state in the left lead, and that thing in the brackets is my C sub n. And we use this form to solve for C1 in terms of C0. We write what C is at site 0. That's the first green equation. We write what C1 is at site 1. That's the second equation in green. Then we multiply through by this whole equation on the left and the right by these two, by e to the I K L A, and then we subtract the second equation from the first equation, because we don't know. RL is unknown. RL is unknown, so we're getting rid of that, right? By subtracting, we're getting rid of one of our unknowns, and we're able to write C0 in terms of C1. And that's what we need to do to truncate this infinite set of equations. Once we have C0 in terms of C1, we have an equation completely in terms of C1. Our equation for row 1 becomes an equation completely in terms of C1 and C2. But what happens when you do that is you pick up this inhomogeneous term, which wasn't there before. Remember, before it was a completely homogeneous equation. Every term had a C in it. And now when you do this, suddenly you pick up an inhomogeneous term. So here it is, we subtract, we pick up our inhomogeneous term. And so this is what I guess over here, this equation here, becomes after you back substitute C0 into that equation for row 1. And the inhomogeneous term I moved over to the right-hand side now. So we pick up an inhomogeneous term, and we pick up this term, which becomes the self-energy, which we'll see in a moment. The term on the right-hand side is a sine Ka, and sine Ka is proportional to the velocity. So this term on the right-hand side is proportional to the incoming velocity. So we rewrote it like that. We went through the same exercise for the right-hand side, and no matter which way, whether you inject from the right or the left, the final form of the equations look like this. So the upper matrix is, the upper set of equations is if you inject from the left. The lower one is if you inject from the right. The only difference is what's on the right-hand side. So going through this algebra, we're able to solve for C0 in terms of C1, solve for C4 in terms of C3, And in that way we can solve for just this device part of the Hamiltonian, C1 through C3, and these extra terms that have showed up take into account exactly the effect of these semi-infinite leads on either side. And these are the exact equations for C1 through C3, which we're going to see in a little bit. We started talking about what these terms represent. These terms on the right-hand side represent the attempt rate to be injected into the device. Since V over A is the amount of time that you spend on any given site, and you can view that as a rate, 1 over tau, and h bar times the rate gives you an energy associated with that rate. Okay, so last time I think we got as far as saying that if you looked at the form of our self-energy, the thing that shows up on the diagonal is equal to, let's see, minus, just to make sure we're clear on the sign, t e to the I, say from the left side, KLA. I think that's right. Yeah, so that would be on for the left, in the upper left block. And if you write this out as like cosine Ka plus, I sine Ka, and work it through, the form of this was some real part and equal to negative magnitude of t cosine KLA minus I gamma L left, gamma L over 2. And this gamma L, which is the same thing that showed up on the right-hand side, the right-hand side term, is, and this is actually a fundamental definition, this is the relationship between the gamma and the sigma, whether this is due to the contacts or whether it's due to phonon scattering or whatever. -2 imaginary sigma. So we have the corner term, the new corner term that shows up in our Hamiltonian, right? We have an E minus like epsilon plus magnitude T e to the I Ka. This new corner term is equal to, by definition, the negative of the self-energy, because we're going to define this in a minute as E minus H minus sigma. This is the form. So just by comparing those two forms, that's why I'm pulling out a negative sign there. So by truncating the system of equations, we pick up this new term on the diagonals, and at the same time we pick up this term, this inhomogeneous term over on the right-hand side of I gamma over on the right-hand side. And so this inhomogeneous term that you're picking up on the right-hand side is related to this new term that shows up in your matrix due to the coupling to the leads. So these are both, both of these things are appearing because of the coupling to the leads. This represents injection from the lead. This is your source term, right? These gammas that show up, this is your source term. This is what you're injecting into the device. And it has a form of a rate. That's really an energy, but it's just an h bar times a rate, v over a, right? This is h bar times a rate converted into an energy by multiplying by h bar. And then on the diagonal of your Hamiltonian, you also have the same term arising. So the sigma, the imaginary part of sigma, or -2 imaginary sigma, is this gamma. So your sigma r has this term in it of I gamma L over 2. That'll be the form of the imaginary part. So the imaginary part of sigma r, or I times the imaginary, to keep it, so is gamma L over 2. Okay? And so I think this is what I started talking about. So if you look at this new effective Hamiltonian that we've created, this guy here, suddenly there's some imaginary terms on the diagonal. And if there are imaginary terms on the diagonal, it's no longer Hermitian. It represents loss, a finite lifetime. And I'm not sure if we got into this discussion. If you just look at Schrodinger's equation, IH bar d psi dt is going to equal p squared over 2m minus I. Let's see, h. I guess this would be just minus I. Yeah.
Sorry, what is the R denote sigma?
Oh, it sounds retarded, but it stands for retarded, actually. Oh, yeah. It's a retarded self-energy. and later we'll see that, everything we're doing is in terms of energy, and the energy is related to a Fourier transform of time. And hopefully we're going to see later that it comes in the time domain, it has this time dependence. So it's only non-zero for times after, for t is coming after t prime, so it's causal. So it's really the causal, we're in a moment going to define a retarded green function along with our retarded self-energy, and then you can think of this as the causal green function. If I injected t prime, I only get a response for some time after t prime. There's no response before t prime, because we'll also run into what they call the advanced green function, which is sort of anti-causal. You get a response before you hit the system. So at any rate, this is where the terminology comes from. You can think of it as the causal green function, and the associated causal self-energy. And actually, we're going to see that in a minute. So if I put in this, I guess, I gamma over 2, I'm going to put an imaginary potential, a constant imaginary potential, into, what would be my Hamiltonian. So let's say my Hamiltonian has that form, right? So IH bar d psi dt is H psi, but now I've just added this, constant imaginary potential, which is what we've just done, right? In this system here with my effective Hamiltonian. If I think of this as some effective Hamiltonian, I now have an imaginary term on the diagonal. So let's just, you look at this to understand what happens when you stick in a constant imaginary potential. Well, you can look at it two ways. If I allow my energy to become complex, which usually you don't do. If I allow my energy to become complex, so it's equal to my usual, h bar squared k squared over 2m, which I'll just write as ek, minus I gamma over 2. Okay. Then my solution would just be the usual e to the I kx, e to the minus the usual time dependent thing you always get, e to the minus I e sub k t over h bar. No different there. But then you get this other extra term, e to the negative, I have t over 2 tau, so what's that? E to the negative, I guess it's going to be gamma, I need an h bar in there. Gamma h bar times time is gamma over, I guess, 2, these darn h bars are messing me up. Gamma t over 2h bar. That would be it. And I think in my notes, I was trying to do this in terms of gamma. But if we let gamma equal to, which is what it is, h bar over 2 tau. H bar over 2 tau. Then the form of this becomes a little more obvious. This is just e to the negative t over 2 tau. Okay. Where tau is the same, 1 over tau is this rate that we were just talking about, like our velocity over a, for example. And so what happens is, as time progresses, if we look at psi squared, as a function of time, it just disappears on you. So this is what happens when you have an imaginary potential, right? Probability is not conserved, right? Probability is not conserved. As time progresses, psi just disappears, just sucked away into nothingness. All right? So whenever you have an imaginary potential represents a finite lifetime. This is a very general truth. An imaginary potential represents a finite lifetime. Because if you think in Schrodinger's equation, the only time dependence of your wave function is just a phase factor, e to the minus I, some real energy, and this just oscillates forever, right? But if you have a finite lifetime, it means probability is decaying, and usually we don't like that because we want everything to be normalized for all time. And if your probability disappears, there's no way it goes to zero. You don't have a normalized wave function anymore. But this happens when you have when you define some finite system that's connected to two reservoirs, which is what we've done. Because now we're just defining probability within the finite system, and obviously that can disappear because it can go into the reservoirs. So because you have this thermodynamic system now, probability, if you put an electron into this finite box, after a while it'll probably not be there anymore. So this is what this imaginary potential that's showing up on the diagonal, this is what it represents. And so this is, something that you've never dealt with before, having an imaginary potential in your effective Hamiltonian. And let's see, is there anything more to... So we have an injection. Let's see, the injection, that we're injecting from the lead, coming from the inhomogeneous terms, has a rate 1 over tau v, say from the left lead, v over a, right? That's the rate of injection. So if this is from the left lead, here's my device, boundary with a lead. I'm injecting with this rate into my device 1 over tau. Okay? Because by definition, I'm sending, the way this problem is set up, I'm sending in a wave e to the I k lx. I'm sending in a rightward moving wave. So it's heading into the device. Okay? Now if I put the decay rate in the device, so this is my lead, This is my device over here. In the device, if I look at the corner term from my sigma here, it's giving me my finite lifetime in the device. So on this node, which is that upper left corner element block, right? I've got a decay rate of the term that went into my self energy was minus I gamma L over 2, which is gives me a decay rate of 1 over 2 tau. That factor of 1/2, 2 in the denominator. Gamma L is 1 over tau, but what goes into my self energy is 1 over 2 tau. Okay? So the decay rate, the injection rate is 1 over tau, coming in from the left. If I put an electron on that site, the decay rate is 1 over 2 tau. The reason is that if I put an electron here, I'm not saying anything about which way it's moving, so it has a 50% chance of going that way, a 50% chance of going that way. It's only if it goes to the left that it decays and leaves the system, and that's why you have this factor of 1/2. Right? Because I'm not defining the velocity, I'm just putting it on that site and asking what's the decay rate. Well, if it moves to the right, it stays within the box, it doesn't decay. Only if it goes left does it decay, and so the decay rate, you get this 1 over 2 tau. Okay, so I think that's pretty much all the story we need for the imaginary part. There's also this real part we haven't mentioned yet. So we got the real part of the self-energy, which is, I guess it's minus T. So let me just write out the self-energy. This is what's going on your, and now I'll give it indices. This is going on that 1-1 block of that matrix, the upper left corner. And so this was negative magnitude of T cosine K A minus I magnitude of T sine Ka. Okay, that was the whole expression, going back to the original way we formulated it. And so now we talked, we just went through the imaginary term in gory detail. Now let's say a few words about this real part here. What is this thing doing? And I guess the best thing is to just plot it. So if we plot this, the real and imaginary parts, so as a function of k, going from 0 is pi over 2a, and pi over a, and this will be magnitude of t, negative magnitude of t, so the real part is going to look like this. It starts off at negative t and it goes up to t and it goes through 0 right in the middle. That's your real part. And your imaginary part starts at 0, it peaks right at pi over 2a. It's supposed to look like a sine function, sorry. Upside down sine function. So this is imaginary sigma, and this is, the blue one is real sigma. So and just to, if you think about your tight binding band, at pi over 2a, you're right in the middle of the band. At 0, you're at the band edge at, pi over A, you're at the top of the band, right? For our tight binding band. So just to recall, our tight binding band, here's pi over A. We have this, so it's just your cosine tight binding band. So pi at 0 is energy K. So at 0, you're at the bottom of the band. At pi over A, you're at the top of the band. At pi over 2A, you're right in the middle of the band. Okay? And so the real self energy is shifting the the site energy. We have E minus epsilon minus the real sigma, right? So that's just shifting that site energy up and down as a function of, there's a mapping between K and energy. So if we write that in terms of energy, as a function of energy, right, I can map between K and energy. So shifting that on-site energy up and down is a function of energy. And it's shifting it in such a way that, we'll go and look at this in a minute, if we were to calculate sort of the energy spectrum just from this 3x3 matrix, we would reproduce exactly the energy spectrum from the entire, infinite problem that we were doing in 208. We're going to get the same wave functions, the same energy spectrum, the same dispersion, and all that. So just by solving the 3x3 with these self-energies in the corner, we reproduce this exact solution of the infinite chain. So they're serving to give you the whole bandwidth, and if we just separate out the 3x3 part of the eigenvalue problem, we would have E minus epsilon, E minus epsilon, E minus epsilon on the diagonal, and then I guess we'll have negative t, negative t, negative t, negative t. But we also have, these extra terms that we learned how to truncate the infinite system into a finite 3x3 system. And when you do that, these terms on the diagonal pick up this new term, which we call the self-energy. So this term becomes E minus epsilon minus sigma r due to the right-hand lead. And this other term up here becomes E minus epsilon minus sigma r due to the left-hand lead. So that's what happens to the 3x3 matrix. Okay, that's how it gets modified, right? And let's just call this modified matrix, we called it H, D tilde. The modified Hamiltonian. So the modified Hamiltonian was just our 3x3 plus the sigma r. That's how we defined our modified Hamiltonian. And so the new matrix looks like, if we define our sigma r as a matrix, where you only have something where there are non-zero terms, so sigma r left, 0, 0, 0, 0, 0, 0, 0, sigma r right. These are the only non-zero terms in that matrix. They only showed up in the upper left, lower left diagonal. And so now if my H sub D is a 3x3 matrix, then this is truly a matrix equation, right? Where I just add this plus my original 3x3, E minus epsilon, minus T, 0, minus T, E minus epsilon, minus T, E minus epsilon. I add them together, or minus T, 0, and we have exactly the equations we derived, just adding those two things together. Well, actually, I got to subtract. Let's see. I'm screwing up the signs. I'm sorry. The form I'm trying to write is E minus H sub D minus sigma r. That's the form we want, because this is going to define our green function. And what I wrote down here is E minus H sub D. This is the matrix I wrote down here, E minus H sub D. And so if I take E minus H sub D and I subtract off, this matrix, I get this. And so the form of the equations that we derive for C1 through C3 look like this. E minus H device, which is just the 3×3 part of our Hamiltonian, minus sigma R, which is that 3×3 matrix I wrote down, acting on C1, C2, C3, is equal to, say if I inject from the left, I gamma left 0, 0. Right? Though that is the form of the equations that we derived. And to be clear, this, sigma, I guess when I define this 3×3, I should have made it clear. So sigma L would be, what would sigma L be? Negative magnitude T e to the I K L A, to be very clear what we mean by sigma L. And sigma R would be the same thing, replacing KL with KR. Okay? And so this is the form of our equation that we derived. And this thing, which you'll learn to know and love, is the inverse of the retarded Green function, by definition. And so the formal solution is C1, C2, C3 equals my Green function times I gamma left 0, 0. All right, just multiplying through by GR. Just to be clear, it's just the R stands for retarded again, because it's a causal Green function. And this is all. So this is this 3×3 matrix. Just to be clear, this is the 3×3 the matrix that we've been looking at. 3×3 matrix. Same 3×3 matrix we were looking at earlier, just written more formally and more abstractly. And this is the general definition of a retarded Green function. Right now, the sigma just represents the effect of those semi-infinite contacts. It includes the loss due to stuff going in and out of the contacts. The gamma on the right side is injection. But the sigma could represent phonon scattering, where you're going along in some eigenstate, you hit a phonon, and you go out of that eigenstate into some other eigenstate. So as far as that initial eigenstate is concerned, you're lost. You disappeared suddenly. There's a finite lifetime which comes about through an imaginary term in the self-energy due to phonon scattering. So anything that takes you out of an eigenstate of this, this ideal crystal shows up as an imaginary term in a self-energy. So this is a very completely general expression for the self-energy, for the Green function, in terms of E minus H minus sigma, and right now that sigma is just including the effect of these semi-infinite leads.